Hello, ladies and gentlemen. How are you? This is from Friday, January the 13th. We've started our new unit of curve sketching a function using calculus methods. There's 6 different characteristics we're going to start looking at. We're going to look at the domain of f of x. We're going to look at intercepts of f of x. We're going to look at whether or not the curve f of x is even or odd or neither of those two. We're going to be taking a look at asymptotes. We're going to look at vertical asymptotes. We're going to use limit charts. So if I have an asymptote at x equals 2, I'm going to use limit charts as x approaches 2 from the left and x approaches 2 from the right to determine the behavior, whether or not it goes to positive infinity or to negative infinity, or to positive infinity or to negative infinity. Can't be both. Got to pick one. And the charts will tell us. We're going to look at horizontal asymptotes. Horizontal asymptotes happen at the extremes of the curve. So we're going to be looking at infinity limits. As x approaches positive infinity this way, you'll notice that this example certainly has a horizontal asymptote of f of x equals 2. As x approaches infinity, f of x would equal 2. And we're going to go one step farther and say that it's approaching 2 from above. This one, notice that we've got a horizontal asymptote running all the way across. The limit as x approaches positive infinity is 2 from above. The limit as x approaches negative infinity is 2 from below. So notice that we can cross a horizontal asymptote. It doesn't have to be in both directions, but it could be. So we need to check both directions of the infinity. And this one, just to give you another example, I could have a horizontal asymptote as limit as x approaches positive infinity. It goes to 2 from below, and this one's going to negative 5 from above. So in general, we're going to be evaluating infinity limits. We're going to see if it approaches a constant. If it does, then there's a horizontal asymptote. If it doesn't, if it approaches plus or minus infinity, we have end behavior. And then we'll use a test point or a little bit of mental math to find out whether it's approaching from above or below. Then we get into the first derivative. The first derivative, remember, tells you the slope of the tangent, which is the rate of change. If the slope of the tangent is positive, in other words, the first derivative is greater than 0, then we have an increasing function. If the slope of the tangent is negative, in other words, we have a derivative which is less than 0, then we have a decreasing function from left to right, from left to right. We're always reading from left to right when we talk about increase or decrease. This is an increasing function. But so is this an increasing function. This is a decreasing function, but so is this a decreasing function. The difference is this one is concave up, this one is concave down. This one is concave up, this one is concave down. The first derivative test will not tell us whether we're concave up or concave down. We will need to go to the second derivative test to do that. This will talk about whether the rate of change is increasing or whether the rate of change is decreasing. Okay, and we'll talk more about that in number 6. Right now, just looking at whether or not we're increasing or decreasing, we will simply look at the derivative, the first derivative. If the first derivative is greater than 0, the slope of the tangent is positive and f of x is increasing. If the derivative is less than 0, then f of x is decreasing. Question: where can a function change from increasing to decreasing or vice versa? So if I go from increasing to decreasing, I've gone from positive to negative, I must go through 0. This point, the slope of the tangent is horizontal. Therefore, the slope equals 0. If I want to know this value of c, I take the derivative, I set it equal to 0, I solve for x. That value is that c value. We call this a local maximum. Over here, let's say I go from decreasing to increasing. Decreasing to increasing. Well, I went from negative to positive, which means f prime at some point must go through 0. The slope of the tangent here is 0. That tangent is horizontal. Therefore, we call this a local minimum. Now, local minimum means that this point is lower than the points on either side of it, directly beside it. This local maximum means that it's its highest to the points on either side of it. And we're going to talk about more about that later. We could also change from increasing to decreasing if there's a vertical asymptote. So I get to lift my pen off the page when I'm graphing this, which means I can come back down and I could be the opposite of what I was doing. So if I was decreasing over here, I could then increase over here. Notice I don't have to change. These are the only times when I can change. The only times when I can change from increasing to decreasing or vice versa is when the first derivative equals 0 or when the first derivative has an asymptote, is undefined. After that, we'll use interval charts to help us with our sketch. The last thing we look at is the second derivative. Now this will tell us whether we're concave up or we're concave down. Notice this is concave up and increasing. This is concave up and decreasing. This is concave down and increasing. This is concave down and decreasing. This, since the rate of change is increasing, the second derivative is greater than 0. This one, since the rate of change is decreasing, the second derivative is less than 0. So second derivative is greater than 0 here. Hold on. Second derivative is greater than 0, so it's concave up. Second derivative is less than 0, so it's concave down. If the second derivative is greater than 0, the curve is concave up. If the second derivative is less than 0, then it's concave down. When can a function change concavity? Either at an asymptote for the second derivative or at what we call points of inflection. Here I'm concave down, there I'm concave up. The second derivative is less than 0. The second derivative is greater than 0, which means at this point the second derivative must have equaled 0. We go from concave up to concave down, so the second derivative is greater than 0, the second derivative is less than 0, so the second derivative at this point must equal 0. And I showed it one more time here. Okay, that was our class. Let's see what I got. So finally, for number 6, we're going to take the second derivative. We're going to determine all the critical values. That's where f of x can change concavity. And that's going to be where the second derivative equals 0 or where the second derivative is undefined. And then we're going to use an interval chart. Using all 6 of these characteristics of the curve, we're then going to sketch the function. I'm going to stop now and I'll do an example with you.